Okay, I guess we can start. So section 3 about topological operators in higher dimensions. Okay. So what we aim to do now is to extend aspects of what we have learned about the symmetry category in 2 dimensions to what can be the symmetry category in higher dimensions. No? So what is the idea? The idea is that in general, in a d-dimensional quantum field theory, is something that produces correlators. No? So interested in correlators of the following form, no? Something like this. Insert a bunch of local operators at some points. Then you can extend also so you can insert also some other type of operators, call them W. And this will be the analogs of the heavy defects that we mentioned at the beginning. On space times X. So X is a d-dimensional space-time. The OIs are local operators inserted at points. And the Wj are extended operators. They are supported along some submanifolds, say. Okay, of dimension, say, Pj. This would be the heavy defects in our heuristic argument. No? So these are the general correlators that we can encounter in a d-dimensional quantum field theory. No? We are familiar from textbooks in expression of this type, where we have only local operators insertions, but we can also insert other operators that are now extended and supported in different along different submanifolds. No? And now the topological operators of various codimensions are structures that give conserved quantum numbers for these W's. And so if we have a good theory of conserved quantum numbers for the Wj's, we can hope to be able to constrain this type of correlators by suitable generalizations of word identities. No? So we can hope So in these lectures, between today and tomorrow, what I will do is to give examples of this kind, and also give you examples of the generalized Ward-Takahashi identities that can occur. No? Notice in particular one thing. No? We mentioned the Coleman-Mandula theorem and the symmetries of the S-matrix. No? The topological operators, they give rise to quantum numbers for these extended defects. No? And the Coleman-Mandula theorem is about features of the S matrix of particles. So it constrains only local operators. And this is why these generalized quantum numbers evade the Coleman-Mandula constraint. No? They don't act on local operators. They act only on extended ones. So in the discussion yesterday, we discussed some examples, but I want to put it here also because it's part of the material of the lectures. The basic example, this comes from this work by Gaiotto, Kapustin, Seiberg and Willett, expressed in this way. No? Are these higher p-form symmetries? And we will denote them like this. We'll discuss the case of U1. No? Of course, one can consider more general cases, but U1 and P is an index. It is the same index as appears there. It denotes the index of the charged defect. No? So they arise whenever your QFT has a conserved P+1 form current. So it's something that has this structure. Okay, satisfies an equation like this, where J is a P+1 form. Okay, so it's a tensor that has P+1 indexes, and they are all antisymmetric. Okay, and it satisfies this conservation equation. Okay. So if you have a quantum field theory that has one such higher p-form conserved current, then you can construct a topological operator as follows. So, and they would be inserted on oh, let's call them D as well, so that okay, where theta is just a parameter, no, on the circle, and sigma D minus P minus 1 is a closed oriented submanifold of X, no, of dimension D minus P minus 1. Now we discussed during the discussion session that the Stokes theorem implies implies that these operators are invariant upon small deformations of their support. And the argument is something we discussed together, so I won't review it. Or maybe but not all of you were at the discussion, no? That's true. So maybe quickly. So the idea is that you can consider like your surface, and you can consider a surface that you have deformed, no, like this, and they will enclose a manifold of one higher dimension, no. So you can call this manifold I don't know, maybe we can call it M, no, of dimension d minus p, no? And this manifold is such that the boundary of M is the difference between d minus p minus 1 and sigma twiddle d minus p minus 1. The difference is just related. I use the minus sign to remind that the orientation of the internal manifold is opposite to the one of the external one. No? And so you see that when you compare the value of this operator on these two surfaces, this one is equal by the Stokes theorem, the integral of d star of j p plus 1 on the manifold in one dimension higher, and since this one is conserved by construction, this is equal to 0. No? Now these operators measure the U1p charges of the non-topological defects. Okay. Of dimension W gamma where so how does it work? Well, the idea is that you take your gamma is a I already said it's a p-dimensional submanifold of X. You can take a ball, say inside of X, it's a d minus p dimensional. And this ball is such that it intersects gamma p exactly at one point. Okay, this happens generically, no? Because the difference in dimension between these two submanifold is 0, and so they will intersect. They will meet at least at a point. And we can always, since we can wiggle the support of our defect as we want, we can always suppose that this intersection is also transversal. And now we consider the boundary of this ball. This is a sphere of the right dimensionality. And we would say that, that WP has charge Q with respect to this defect. We say that has charge Q under this U1 P symmetry if in correlators under these conditions okay. So you see, like, I try to spell on the board the condition that define the linking number. No? So you have your sphere, and you are inserting your operator along a line or a higher dimensional surface. No? And your sphere, this is dimension p, this is dimension d minus p minus 1. The ball is the interior of this, and your submanifold intersects it exactly at one point. No? And we say that W gamma has charge with respect to this topological defect, provided that if you are in this configuration, this identity holds in correlators. Okay? So let's see an example of this. In the context of Maxwell theory. No? Maxwell theory is just the usual the usual Maxwell theory. No? The only degrees of freedom, it's a free theory, conformal. No? The only degree of freedom is a U1 connection. It has curvature that locally can be expressed as a differential of a one form, no? But it is subject to gauge transformations. So you can always shift A1 by the differential of a scalar, no? This is gauge symmetry. And now, well, the idea is that this theory enjoys a pair of one-form symmetries. One is electric and the other is magnetic. No? I'm reviewing this also so that we set some notation for tomorrow. No? And so what are the corresponding Higher form currents? So the electric Higher form current is just given by the gauge connection itself, and the magnetic Higher form current is given by the Hodge dual of the connection divided by 2 pi. And they are conserved precisely because of the equation of motion. So and this is conserved because of the Bianchi identity. Okay. Now, what are the corresponding charged operators? So remember that we want our topological defects to act faithfully, so they have to act on something. Topological operators are the Wilson and the 't Hooft lines. No? So they are defined in this way. Topological defects are defined as the board that I just erased. No? And so the Wilson line is just a holonomy for the Maxwell field. Okay, something like this. You can think of gamma as if it is the word line of an infinitely heavy electrically charged particle with charge QE. No? And the 't Hooft line, from this perspective, we have to define it as I sketched the other day. So the idea is that to define it, we have to consider gamma, remove a tubular neighborhood around it, and along the prescribed boundary conditions for the fields of our theory. In our case, we only have the gauge field to prescribe. We are in 4 dimensions, so there is an S2 that links this cylinder that we have removed from space-time, and we prescribe that f over 2 pi integrated on this S2 is equal to Qm. No? This is a 't Hooft line. Okay. So now we want to verify that they admit they are really charge QE and QM respectively with respect to the topological defects associated to these conserved currents, no? In correlators. Yes. Is defined as I said, is defined with words, no? So it is a line, no, along which we have removed a cylinder out of space-time, and we have prescribed a boundary condition for the Maxwell field on the spheres that links it in such a way that it carries a magnetic flux, no? So it's defined in this way, from this perspective. Then tomorrow, I think we will discuss electromagnetic duality for Maxwell theory, and from that perspective, we will see that the 't Hooft line is exactly like a Wilson line, but for the dual photon. But we will do it tomorrow, so don't worry. Okay? So let's check that this definition is really working. So, well, yes. Hey, yes, that's it. That's how it is defined. No, inserting a 't Hooft line is means doing this. It doesn't have an expression in terms of the electric variables. No, so it's defined in this way. No, yes. What is a capital F? Oh, I'm sorry. It's a typo. Thank you. This is why people were confused. Thank you very much. Okay, so how does it work? Well, for the magnetic case, the standard notation is that the magnetic one-form symmetry is denoted with the symbol eta, m and theta, inserted around S2. No, this will be just the exponential of I theta integral over S2 of star of J2 magnetic. No, but you can see from how it is defined that this equals the integral over S2 of the F2 over 2 pi. And so, of course, by definition, when we insert it in correlators, if we act with this, if we are in a situation where the S2 is exactly like that, then by construction, this will transform like e to the theta qm wqm because of the definition. No? The S2 which links the 't Hooft line is exactly the one where we are inserting the magnetic defect. So for this one, it works by definition. For the Wilson line, it requires a little bit more work. Yes. Yes, it is the standard notation for this. It would be d1 m theta in the. It's the standard notation for the one-form symmetry. They are called eta in many papers. So. And well, for the electric one, no, we want to prove that this is true. no? Inside correlators. No? So how do you do it? Well, the idea is that if you consider a correlator where you have inserted a Wilson line, you can expand it in the path integral. No? So we have the path integral over the Maxwell field. No? And then we have the usual, no? We have the exponential of the action of Maxwell. No? And then, since we are inserting this gadget, well, we can exponentiate it, and it will become the integral of this times QE integrated over gamma of A1. No? But notice that now that we have inserted this, so we can perform a manipulation of this expression. So this is integrated over x. This is integrated only over gamma. So we can rewrite it as EQE integral over x of A1 times a three-dimensional delta function supported on gamma. No? More mathematical terms, this would be the Poincaré dual, the form associated to the cycle of gamma. No? Oh, sorry, yes, it's in the path integral, sorry. Yes. No? So this is the path integral measure. So you see that inserting a Wilson line, no, by this equation, it has the effect of changing the equation of motion for the field, for the Maxwell field. No? Yes. It's a Poincaré dual of this one cycle. No, it's a whenever you have there is a duality between cycles and forms. No, you can think of it just as a three-dimensional delta function supported along the line gamma. No, it would set your integral to 0 unless you are supported along a gamma. No, and you see, like this expression here looks exactly like the coupling of your gauge field to a current. No? A current associated to an electric particle of charge QE. No? It's just the minimal coupling. And so you get a new equation of motion, which is the equation of motion that you would get if you had a charged electron in the game, which in this case is just this one. No? And this equation modifies the equation for the conservation of that current. No? Wedge is the wedge product. Yes, yes. So there is a natural product by which you can multiply forms. Yes, okay, yes. So from this, we see that we have an action as the one that we desire above, no? Because again, exploiting the relation between the current and F, no? We see that integrating star of JE on a surface, no? Would receive a contribution proportional to the electric charge only when the surface enclose the support of the operator. No? So if we fill in the ball that we were after, as we discussed at the beginning, if we fill it in, then the integral will be non-zero only if gamma is intersecting the ball at one point. No? So From this it follows that the action of the U1 electric one form symmetry captures the electric charge of the Wilson line. Okay. Now, yes. Uh, well, yes, the structure of the topological defects that you obtain changes according to the theory that you have, no? So well, you need the conservation of the current to be true within correlators. No, all the equations that I write have to be true within correlators. No, so we will see later examples where you get other types of conservation equation within correlators, and you will obtain corrections or the structure of the topological defect that you obtain change. No, so it is the quantum equation that matters. No, in this case, the classical and the quantum equation are the same because it's Maxwell theory. No, but in general, it is the current conservation within the correlators that is the question that you have to look at. So in particular, if there are ABJ anomalies, you will have to keep track of those, and they will have interesting effects. And hopefully today we will see some of that. So it is interesting to remark in this context that these symmetries are spontaneously broken. So and the corresponding Ng bosons will have spin. This is related to the fact that if we consider backgrounds for these symmetries, they will be higher form fields. And so in particular, we have two of them that are broken, and they correspond to the two polarization of the photon. Okay. So this is maybe a good moment to comment about a question that I received earlier. There is a Coleman-Mermin-Wagner theorem for U1P symmetries. And it says that Higher P-form symmetries cannot be when D minus P is less than or equal than 2. Okay. So well, this is already an interesting remark, no? That there is a symmetry reason for the masslessness of the photon. I remember I was really surprised and when I read it for the first time. But there is another remark, which is that it's related to a remark that we got during the discussion session today, which is that it can happen that your operator of charge Q, say W of gamma, ends along a p minus 1 dimensional operator. No? If that happens, for a higher p-form symmetry, we have an identity in correlator that has the following form. No? This is your W gamma. This is the place where it ends. It ends along an operator inserted on a p minus 1 dimensional cycle. No? It's your correlator. And to measure the charge here, you have to link this with this dp symmetry defect inserted around the appropriate sphere that links it. No? And you see that from the action, we get an equation by shrinking the defect, the topological defect around it. We get an equation like this. To the I theta q. Q is the charge of this extended operator. No? And this one is just the same configuration. But then, since it ends, we can slide the operator out. No, can slide it out. Oops, sorry. And we can shrink it, and now it doesn't wrap anything, so it gives rise to no action whatsoever. No? And so we end up with an equation like this. No? And so you see that this correlator can be non-trivial only if this phase is equal to 1. Which in particular implies that theta has to be 2 pi over q. No? And so if this happens, then we have an instance of screening. So the U1 p-form symmetry gets broken to a ZQ subgroup. No? For instance, this happens if you couple your Maxwell field to some charge Q electrons. No? And you will break the electric one-form symmetry to a one-form symmetry subgroup. No? So this was a P. Okay. One way to argue for it is that when you insert the curvature f in a vacuum expectation value, no, you know that you obtain the photon propagator when you quantize the theory, no, and so it says that the symmetry generator, because the curvature of the field is the symmetry generator, has a non-trivial matrix element in the vacuum, no? Which is the hallmark of a spontaneously broken symmetry, no? And the particle which is created is precisely the photon. And so the photon is an Ambu-Goldstone boson. Thank you for the question. So another example of this type, so in this way, you see, you get, you obtain finite versions of higher p-form symmetries. No? Just by screening. And an example, a very interesting example where this happens is in the context of Yang-Mills theory. Yang-Mills theory consider, for simplicity, the gauge group SUN, no? This theory will have a one-form symmetry which is just a Zn, which is associated to the center of SUN, no? And the reason why you get such a symmetry is that if you consider pure Yang-Mills theory, no? Pure Yang-Mills has charges only in the adjoint representation. No? And the charges in the adjoint representation commute with the center of the group. So they cannot screen. The only part, the only higher form symmetry part that survives is the center. So in particular, there are charged operators in this context which are given by the Wilson lines, no? Wilson lines in Yang-Mills theory. They are defined in a similar way. So they are defined as traces in a given representation of the holonomy of your gauge group along a curve gamma, no? So they are non-abelian versions of the Wilson lines in Maxwell theory, no? And precisely because of the screening mechanism, you can only see the so-called n-ality of the representation as a charge. And this is related to the screening that we discussed, no? Because you have operators charged in the adjoint, you have all the charges of the adjoint in the game, and you can insert them along the Wilson lines, and in this way screen the symmetry down to the center. So in reality, so this looks like a lot, but there is only n independent Wilson lines. Up to screening. And they are labeled by their n-ality, no? Which is the charge with respect to this Zn center. Now, these are interesting because they have an interesting interplay with the spontaneous symmetry breaking. So if a one-form symmetry is spontaneously broken, the line defects are deconfined. And if instead it is unbroken, then the line operators are confined. Line operators no? So the idea is that the order parameter for the spontaneous breaking is the VEV of the corresponding Wilson line, no? And so in SUN in particular, these VEVs exhibit area law. And this implies that the symmetry is not spontaneously broken. So to understand this, maybe it's worth to do the argument in general. Yes. Yes, let me discuss it in more detail 1 second. I just realized that I skipped part of my notes. So the idea is that so in general, when you compute the expectation value of an extended operator like this, no, it will scale like the exponential of some function of the support of this operator, no. And now, if you want to measure whether a symmetry is spontaneously broken or not, no? If it is spontaneously broken, this means that at infinite volume, no, there is some order parameter which takes a VEV, no? So what is an order parameter? An order parameter is an operator which is charged with respect to the symmetry, no? If a charged operator with respect to the symmetry has a non-zero VEV, this is a hallmark of the symmetry breaking, no? So as we scale the volume at infinity, we have to consider what happens to this VEV, no? And the idea is that in the process we have to send the volume of the surface where we have inserted our extended line to infinity as well, no? And one has to consider this ratio, the ratio between this dependence, which is computed explicitly, and the volume of the support of the extended defect, no? And in this limit, there are essentially two options, no? Either this limit stays finite, and therefore one has a spontaneous breaking, or this volume goes to infinity, and in this case the symmetry stays unbroken, no? The idea is that if it scales in this way, we can rescale the operator that we have defined, no, with an appropriate term, such that in the infinite volume limit, this VEV is non-zero, no? Yes. We can redefine this operator, no, by inserting some sort of a counter term supported only along its volume, no? And so for Young Mills, this is what happens, no? So you can see that you have this type of behavior, which is the area law. So so we've seen these higher form symmetries have various features, and we can compute them, and they have features that are reminiscent to features of ordinary symmetries. In particular, they have order parameters, and they can be spontaneously broken or not. And if they are spontaneously broken or not, that has interesting consequences on the dynamics of the field theory. No? In particular, we can also gauge them provided there are no anomalies. So how do we detect anomalies of these higher P-form symmetries? We detect them essentially in the same way we detect anomalies of ordinary symmetries. So we detect them by coupling them to backgrounds. So in particular, let's consider the case of Maxwell as an example. And you have your electric one-form symmetry and the magnetic one-form symmetry. And in this case, the background will be a two-form gauge field, and another one for the magnetic. The fact that they are two-form gauge field means that their gauge transformation are one-forms. No? And then there are further enhancements. No? There are gauge transformations of gauge transformation and so on and so forth. No? But naively, we can think of them as just higher form gauge fields like this. And if we do that, so the way in which we can deform the Maxwell action in presence of backgrounds is essentially dictated by minimal coupling. No? So by minimal coupling, we obtain an action for the Maxwell field in presence of backgrounds of the following form. No? Call it B2E, B2E. And then there is an extra term for the magnetic background. And now to detect if there is an anomaly, we have to check whether the path integral stays invariant under a background gauge transformation. Okay. So in particular, we want to consider what happens if we take our Maxwell theory action and compute a gauge variation with respect to these one-forms gauge fields for the electric and the magnetic backgrounds. And you can try to check as an exercise that the difference between this and the original action has the following form. So So and it is impossible to get rid of this term by local counter terms in the by adding local counter terms to the action, which are just functions of the background fields. So you see that what this equation says is that in presence of a non-trivial background for the magnetic one-form symmetry, the gauge invariance with respect to the electric one-form symmetry is gone. And so this is the hallmark of what is called a mixed anomaly. No? There are mixed Tuft anomaly between U1 electric and U1 magnetic. No? One cannot gauge both symmetries simultaneously. One can gauge the electric one or the magnetic one separately, but one cannot gauge both. And there is also an IC inflow action for this mixed anomaly that has the following form. So remember from the lectures about anomalies that if you have an anomalous quantum field theory, you can always think about it as if it is the boundary of a higher dimensional field theory, no? Which is just a classical function of the backgrounds. No? In this case, the function will be the exponential of this. No? And here you have your Maxwell action coupled to the backgrounds. Okay. Okay. Maybe we can have a break and we can continue in 10 minutes. Is that okay? Okay. So, yeah, so in this way we can detect this mixed Tuft anomaly. No? When they are not anomalous, we can gauge them. No? And there is a remark, which is that when one gauges a higher p-form symmetry, one always obtains a dual symmetry back. So you gauge one symmetry, you obtain another one. No? And the degree depends on whether the form that you are gauging is continuous or finite. So for instance, for the finite case, if we gauge a Zn p-form symmetry, we end up with a dual Zn d minus p minus 2 symmetry. No? So in particular, there are certain dimensions where so for instance, when in the context of this morning discussion, we have seen that we wanted to say that if we take the Ising model, no, and we gauge the Z2 symmetry, we establish a duality with the Ising model, no? But in this context, we have a Z2 symmetry. We know that there is a Z2 zero form symmetry, which was the one generated by this eta, no? And so if there is this duality, then also this model better have a Z2 symmetry, no? And in this context, we are in two dimensions, no? These were zero form symmetries. And so you see that gauging a zero form symmetry in two dimensions gives back the same zero form symmetry in the gauged model. And in particular, this type of relation is satisfied also for one form symmetries in four dimensions. So if you gauge a Zn one form symmetry, you end up with a dual Zn one form symmetry back. No? This remark will be important tomorrow when we will discuss duality defects. So and the gauging in this context follows the same logic as we sketched this morning. So gauging a finite symmetry, in this case is a Higher P form, no? Involves decorating your space-time with a consistent network of defect and summing over all possibilities, no? So it's very similar to what we have done when we have constructed the gauged version of the Ising torus partition function. No? So in particular, gauging a finite Higher symmetry is a topological operation. It's a topological manipulation of our field theory. No? When we are used to gauge one form symmetries, no, to gauge zero form symmetries, to gauge ordinary symmetries. No? Typically we gauge them when they are continuous, and when that happens, we have to introduce kinetic terms for the gauge fields, and the theory changes radically. No? There are more degrees of freedom once we have gauged a continuous symmetry. But in the context of finite symmetry, this doesn't happen anymore, no? Because there is no kinetic term for a discrete gauge field. And so the operation of performing this gauging is just some sort of a topological manipulation. It doesn't really changes the dynamics that much. No? It's still very interesting, but it's a topological manipulation. And for this reason, there is an interesting variation on the theme where one gauges Higher form symmetries on submanifolds. So what is the idea? No, the idea is if you gauge if you have your space time, no, x, and you want to gauge it to gauge your symmetry on the whole of space time, you just find a convenient triangulation of the manifold, and you decorate it with insertions of these defects, no, and then you take a sum over all possible decorations, no. Schematically, one can draw it like this, no, and the defect that you insert here are exactly analogs of the sum over all possible generators that we wrote for the um, in the case of Ising. So they are these objects that are called algebra objects. No? So these projectors that we discussed. No? So we decorated with those. No? So since this is a topological operation, we can also consider just performing it on a submanifold of our space-time, no? Of the right dimensionality, no? So of course, p-form symmetry defects, no? This dp theta of sigma, they live no, they are inserted along manifolds that have dimension d minus p minus 1. No? So as long as your submanifold is such that it can fit this type of insertions, then you can consider gauging this symmetry, if it is possible, on a submanifold. No? And this operation generates further collections of defects, which are called condensates. So whenever you have a finite, p-form Higher symmetry, it typically doesn't come by itself. It comes together with a whole collection of other topological defects that are obtained by gauging it on all possible submanifolds that can contain its Higher gauging. Okay. Of course, there are also obstructions to this operation. Which are called Higher anomalies. So sometimes it might be possible to gauge a given Higher symmetry in a given dimensionality, but you change the dimensionality and there is an obstruction to gauge it in that dimension. No? Yes? Yes. So it is a very good remark. No? So the idea is that decorating decorating your space-time with insertions of these defects, of these Higher form symmetry defects, is equivalent to turning on a background for the finite symmetry, no? And summing over all the possibilities is the same as gauging it, no? So in this context, these condensates are doing exactly that. So you turn on a background which is supported on a submanifold, and then you gauge it, but you gauge it only on that specific submanifold. No? And so you end up with a large family. No? If there are no obstruction, if there are no Higher anomalies, one ends up starting from a given p-form symmetry with a large families of defects, which are these condensates. No? And however, the condensates are kind of strange types of defects because they are, you see, they are porous. No? So since the decoration of the condensate with respect to these insertions of higher p-form symmetry defects is topological, no, we can always enlarge the mesh of this line operator, for instance, to let a local operator go through it, no? So say that you have a point-like operator OX inserted in your space-time here, and you move the condensate. The condensate, since it's obtained by a decoration of higher p-form symmetry defects, will not detect this operator, will not cross it. We can always poke holes in our condensate to let it go through, no? So we can move it across, and it will not detect local operators. So also condensates only act on extended operators. Okay. And well, there is a deep interplay between the theory of obstruction, these Higher anomalies that define condensates, with a work by Carkerville and Rankel on the theory of Higher or befoldings, which of course I won't have time to discuss, unfortunately, but they are interesting ingredients in the world of topological defects. If you want to have an intuition about this Higher anomaly, you can think about when we discussed when we have discussed the gauging in 2 dimensions, no? We had considered an obstruction that was related to the S transformation. Do you remember? There was a non-trivial F symbol relating to tori, no? You can consider a triangulation of your manifolds, no? And these backgrounds for the higher symmetries, they will be inserted along the dual of the triangulation, something like this, no? So this F symbol relation that we have brought down above is equivalent to a change in the triangulation, by which we slide the defect and we transform it in this way, no? So you can think of this operation happening smoothly and topologically, no? And the fact that there is no F symbol associated to this change is the statement that we can perform a gauging of that symmetry, no? Now, for higher p-form symmetries, there are similar moves which are associated to changes in the triangulations of higher dimensional manifolds, no? In 2 dimensions, the surfaces can be just triangulated with the simplexes are just triangles, no? But in higher dimensions, the simplexes that you use to triangulate your manifolds becomes higher dimensional versions, no? So for instance, in 3 dimensions, a basic simplex would be like a little pyramid, no? Made like this, no? And associated to these pyramids, no, there are possible moves. So, for instance, this is a possible triangulation of this cube, and you see that there is another one given by 3 triangles, three of these prisms that meet along a central line, no? So this is a move that takes a network it's diciamo, this move is a move that in higher dimension generalizes the flip of the triangulation here, and there is a deep relation between the possible the possible Packner. These moves are called Packner moves. There is a deep theory relating the possible Packner moves in changing the way you triangulate your manifold, and higher versions of the F symbols. Okay, so let's say it like this. And generalized versions, associators. Let's call them associators. So this goes in the theory of higher or befoldings developed by Karkeville and Rankel. So in particular, this higher notion of anomalies arise by considering the interplay of these types, this type of moves with possible networks of topological defects. No? I'm sorry, I won't have time to discuss it at the level of detail I was prepared to. Just remember that there is a theory, or it is interesting to develop this theory. It has been developed in some examples, and we will see. There is a general mathematical theory, but its translation into the physics of topological defects is ongoing. So okay. So for the case of so yes. Sorry. Yes, I'm I'm trying to to condensate my notes, but so the idea is that whenever you have these finite higher form symmetries, you can form the condensates. The condensate give rise to another collection of topological defects, and they have interesting actions. But they come also with a theory of higher anomalies. No. Now, in the case of finite higher p-form symmetries, one can explicitly compute these higher anomalies, and there is a deep theory developed by Karkeville and Rankel that explains how to do that in detail. No, and essentially, like the philosophy is very similar to what we have discussed here. No, so. In the case of the two-dimensional CFTs, you want to require that the corresponding F symbols are trivial. No? For these higher p-form symmetries, there are analogous generalizations of these higher versions of these F symbols, which are associated to so here the F symbol correspond to a change in the triangulation, and in higher dimensions, the change of the triangulation is associated to different ways of decomposing your manifolds in terms of higher simplexes. No? And the structure of these changes is related to structures of generalized associators. So you remember in the first lecture we introduced the F symbol in terms of a diagram that captures the associativity of the fusion product. No? And the higher the dimensionality you look at, the more interesting associators there are. No? So as an example, so if you take the associativity that we discussed for the fusion of lines, no, correspond to a diagram of this type. No, this is the when we discuss the case in 2 dimensions, there is an F symbol relating these two collection of lines. No, but if in the context of a higher dimensional theory, we can consider we have more space for our topological defects to wiggle, say, and so we can consider forming a diagram like this, but now in higher dimensions. No? So this thing will happen behind, this thing will happen behind, this goes up, no? Something like that. And then we are deforming our defects in such a way that this one ends up here and this one ends up there, no? Like this. So this one is in front. No? Something like this, no? And they are crossing here, no? So I hope I have drawn it correctly. But the idea is that you see here we have a diffusion of 3 lines. No? Here 2 and 3 are coming together here, and here we get the 1, 2, 3 collection. No? And here we have 1, 2, and 3, and 1 and 2 are coming together before. No? So while in 2 dimensions, the relation between these 2 diagrams is related to is given by an F symbol, is a change of basis. No? In higher dimension, the associativity of the product can be tracked to higher codimension intersections. No? I'm drawing in a very complicated way the fact that 3 planes always intersect at a point. No, and what happens is that so you can always take care of the associativity just by folding your defects, and the more defects you bring in, the higher the condimension of the intersection that you will obtain. Okay. So in the case of 2D theories, just the multiplication happens at points, at topological points. But for higher p-form symmetries, the higher fusion product happens along surfaces, and these surfaces will develop interesting intersections. Okay. Now the analog of the F symbol for these higher dimensional configurations will be tracked by this type of higher intersections. No? And these higher intersections are what gives to the topological defects a higher structure, if you like. So the simplest example of a configuration that has such an higher structure is given by higher groups. So higher groups are cases in which, say, a zero form symmetry and a one form symmetry mix. No? So far we have discussed U1 symmetries of a given kind, which are associated to conserved higher p-form currents. No? But it can happen that, you see, for instance, in this case, here we have the insertions of 3 zero-form symmetries. They meet at higher codimensions, but along in this point where they meet, they emit a one-form symmetry generator. No? This would be zero form, and they would create a one form at the junction. So higher groups would be an example of this type. So let me conclude with an example of a Higher group. I'm sorry, this was disconnected. I'm kind of falling apart. So how do we detect a Higher group from Higher currents? So we have a higher one-form symmetry associated to a conserved current of this type, but the current associated to the one-form symmetry is no longer, does not obey a usual conservation equation, but instead it satisfies an equation of this type, no? Where this one is a background for the zero-form symmetry. So you see that whenever this happens, there is a mixing between the one-form symmetry and the two-form symmetry, which is triggered by turning on the background for the zero-form symmetry. No? So it's a bit hard to visualize it, but when you have a continuous higher form symmetry that have currents that satisfy an equation of this kind, this can give rise to a non-trivial diagram like this. So So how do we construct an example of a theory that has a higher group of this type? No? So this equation, if you look at it, is a little bit reminiscent of an ABJ anomaly, no? So which you have seen. So if you have a theory that has two U1 zero form symmetries, let's call them A and C. You can consider the possible ABJ anomalies that they can develop, no? And we would have, with respect to their background, a behavior of this kind, no? So these coefficients that I'm calling k are the values of the ABJ anomalies, no? So with so these arise from these triangle diagrams, no? Where you have an insertion of A, and then maybe in this case you have three insertions of A. In this case you have an insertion of A, and then another insertion of A, an insertion of C, and so on, no? Okay, so we are in 4 dimensions. No? For dimensional example, we take a theory with an ABJ anomaly of this kind, no? And so if it is possible to gauge the U1 zero form symmetry, then it will give rise to to a different theory, no? Where we can hope to generate a higher group current algebra of that type. So for that to be possible, the only thing that we need is that the coefficient of the quadratic term over there vanishes. No? So this is possible. This is possible provided, well, the U1 C0 in the original theory is not anomalous, and the coefficient k a c squared is 0. No? Okay. So one can easily engineer examples of this type, no? So we can start, for instance, for a theory that has a 4 Weil fermions with charges, say, Q1, Q2, Q3, and Q4 with respect to the U1A zero form symmetries, and charges Q, Q, minus Q, and minus Q with respect to the U1C zero form symmetries. So you can choose these charges, these are Weil fermions, in such a way that the U1 zero form symmetry has no anomaly and can be gauged, no? And then, well, the other coefficient in the anomaly, no, will be, say, KAC squared will be something like Q squared times Q1 plus Q2 plus Q3 plus Q4. And then we will have K of A squared C, which goes like Q times Q1 squared plus Q2 squared minus Q3 squared minus Q4 squared. And then we have the coefficient Ka cube, which goes just as the cube of the charges, no? And imposing that this coefficient vanishes is just a restriction on the charge assignments with respect to U1A for these Weil fermions, no? And we can always solve it. So in particular, we would end up with an anomalous equation here, where this coefficient is 0, and we could gauge this U10 C form symmetry to obtain a theory that has a subsector which is of Maxwell kind, and therefore upon gauging it develops a magnetic one-form symmetry, no? The one-form symmetry associated to the Maxwell field that we obtain upon gauging this U1 zero form symmetry, no? And if you remember the definition of the magnetic current for this Maxwell field, you will recognize it here. And so, as long as we can, um, kill also this term, and we can do it by choosing suitably the charges, we will end up with a with a higher group structure out of it. Yes. Yes. So yes, so if we restrict, so the idea is that you take a theory with four Weil fermions, it will have and two zero form symmetries of this type that acts on them, that give them charges. Charges are assigned according to this table, no? And it will have a collection of ABJ anomalies, no? The ABJ anomaly will be parameterized by these coefficients that are a function of the charges of this type, no? which follows from computing the various triangle diagrams. And if you want to obtain an equation like that, you can always tune the charges in such a way that it is realized, no? And yes. KAC square is an anomaly coefficient, no? So we have to choose the charges in such a way to design, like the aim is essentially to show that it's easy to cook up examples of four-dimensional gauge theories that have a higher group type of current algebra, no? And the way to do that is to start from a parent theory that has the right anomaly coefficient and has a zero form symmetry that can be gauged, no? Um, I think it's a good moment to stop before I collapse.